In this video, I want to introduce synthetic strategy. And show you how you can make use of the relatively few reactions that you now know to prepare relatively complex structures. So let's say, for example, that we wanted to make three-methyl hexanol. But we were told that all of our sources of carbon must come from either methane or ethane. So we're to start with 1 and 2 carbon building blocks, CH4 and C2H6, but we're trying to make a molecule that contains 7 carbons. So we're obviously going to need to make some carbon-carbon bonds in the process of converting methane and ethane into 3-methyl-3-hexanol. This is largely an academic exercise. You're never actually going to use hydrocarbons as your starting materials because we can readily purchase alkyl halides, we can readily purchase alcohols and carbonyl compounds. But it's an intellectual exercise that's useful to figure out how we can take methane and ethane, simple hydrocarbons, and build up a complicated structure using a relatively small number of reactions. The reactions we're going to need are free radical halogenation, because that's the only way you know to functionalize an alkane. Alkanes can be burned in a combustion reaction, but that's not helpful. They can be pyrolyzed to generate smaller alkanes from larger alkanes, but that's the opposite of what we're trying to do here, which is build up a more complex structure from simpler structures, and they can undergo free radical halogenation reactions. Second reaction we're going to need is conversion of haloalkanes bromo or chloroalkanes, because those are the ones that we can make by free radical halogenation, into organometallic reagents. This will give us a source of negatively charged carbon, whereas free radical halogenation gives us a source of positively polarized carbon. Carbon-carbon bond-forming reactions are going to occur when we take a negatively polarized carbon and react it with a positively polarized carbon. The only carbon-carbon bond-forming reaction you know is the reaction of organometallics with carbonyl compounds or epoxides, which means we're going to use that class of reactions to form all of the carbon-carbon bonds that we see in our product. We're also going to need the oxidation of alcohols, carbonyl compounds, currently the only way we know to make carbonyl compounds. Chromium-6 reagent, which will provide us with the other starting material. Their organometallics are going to come from the haloalkanes, which in turn come from the alkanes, and the carbonyl compounds are going to come from alcohols. And the fifth reaction we're going to need is the preparation of alcohols from alkyl halides by SN2 and SN1 reactions using oxygen nucleophiles. So with just 5 reactions, free radical halogenation, insertion of a metal to form an organometallic reagent, reaction of organometallics with carbonyl compounds, oxidation of alcohols to carbonyl compounds, and preparation of alcohols from alkyl halides using nucleophilic alkyl substitution reactions, we can build up a quite complicated tertiary alcohol starting with really simple building blocks. So how would we proceed to analyze this problem? Generally, the first thing you're going to want to do is some sort of retrosynthetic analysis or retrosynthesis and to identify which carbons in the product come from which building blocks that you're provided with. You'll notice that our main chain is 6 carbons long, so it would be logical to imagine that each of the adjacent 2 carbon units probably came from ethane. So these 2 carbons came from one molecule of ethane, these 2 come from another molecule of ethane, these come from a third molecule. The single CH3 here almost certainly comes from ethane. If we use that analysis, that can help us identify which carbon-carbon bonds we need to form in our synthesis. We need to form the carbon-carbon bond here between carbon 2 and carbon 3. We need to form the carbon-carbon bond here between carbon 4 and carbon 5, and we need to form a carbon-carbon bond here between carbon 3 and carbon 7. So we're looking at 3 carbon-carbon bond forming reactions, all of which are going to start with an organometallic reagent and react with either a 3-membered ring ether containing oxygen and epoxide. Then we can start working backwards and ask ourselves, what are the immediate precursors that are necessary in order to form the carbon-carbon bond? This is a tertiary alcohol. And we know that tertiary alcohols come from ketones by reaction with organometallics. Well, we have 2 choices, because there are 2 new carbon-carbon bonds that are being formed to the carbon that's there as a tertiary alcohol. So we can either work backwards by breaking the carbon 2, carbon 3 bond, or the carbon 7, carbon 3 bond. Each of those is going to suggest a ketone. In one case, if we break the carbon 7, carbon 3 bond, we would want to start with 3-hexanone. And we would want to start with a methyl Grignard or a methyl lithium. Conversely, we could break the carbon 2, carbon 3 bond, and if we did that, we would going to start with 2-pentanone. And an ethyl grignard or ethyl lithium reagent. Either of those two reactions will generate the tertiary alkoxide, which upon acid workup can be converted into the tertiary alcohol. The method at the bottom here is superior because it's what we refer to as a more convergent synthesis. The two building blocks are more similar in size. Which means that we're building up greater complexity in that reaction by converting a 5-carbon and a 2-carbon molecule into a 7-carbon molecule than we are in this reaction where we already have a 6-carbon alcohol and we're adding just one additional carbon. As it turns out, for this synthesis, it really doesn't matter because we're starting with such small materials that neither synthesis in the end will be much more convergent with the other. But let's work with the bottom set, since it is slightly more convergent. And now the synthesis problem has been converted from how to make 3-methyl-3-hexanol to how to make 2-pentanone. We know how to make ethyl magnesium bromide. That's easily available from bromoethane. Work backwards, bromoethane, and then to ethane. We know that we can convert ethane into ethyl magnesium bromide by free radical bromination and simply add magnesium. So we can actually turn around and go back in the forward direction. Reacting ethane with bromine under light initiation. We'll generate ethyl magnesium bromide and HBr. And reaction of bromoethane with solid magnesium in ether solvent. Generate the ethyl magnesium bromide to begin with. We could actually have started, since we know that free radical halogenation is the only reaction we know for incorporating a functional group into an alkane, we could have just said, well, let's brominate everything. And let's convert all of our bromoalkanes. I'll use lithium and THF instead of using magnesium and ether. They're functionally equivalent to make methyl lithium. Right? So I can have an ethyl anion and a methyl anion that can be used to make carbon-carbon bonds. This would be what I would need it to go from 3-hexanone and alkyl lithium or an alkyl magnesium bromide to the final product. So now the problem is, where did the 2-pentanone come from? And the only way we know to make carbonyl compounds is from the corresponding alcohols. And we know that ketones come from secondary alcohols by oxidation with chromium 6 reagents. So we know that in the form 2-pentanone from 2-pentanol. So now the problem becomes, where do we get 2-pentanol from? So now we're confronting a problem that's somewhat similar in concept to the initial problem, except This time we want a secondary alcohol, but we know that secondary alcohols come from aldehydes through reaction with organometallics. Just as in the previous case, there are two different ways we could break this up, depending on whether we want that carbon-carbon bond or that carbon-carbon bond to form. So we could either create this from acetaldehyde and a methyl organometallic, or, sorry, from acetaldehyde and a propyl organometallic. Or from a methyl organometallic and butanol. This is a 3-carbon building block. And our initial starting materials are either 2 carbons or 1 carbon. So a 3-carbon building block is actually, in this case, it might make more sense to start with a 4-carbon building block, which will come from 2 molecules of ethane, and a single carbon building block, which we've actually already made here. We have methyl lithium. So now our problem becomes how to make butanol. And the only way we know to make aldehydes is by oxidation of primary alcohols. So butanol came from 1-butanol. So our problem is now how to make 1-butanol from 2 molecules of ethane. At some point, the oxidation has to be introduced into the molecule. So how are we going to make 1-butanol from ethane? Well, we know that we can make primary alcohols through a 2-carbon homologation by reacting an organometallic like ethyl magnesium bromide, which we have already made, with an epoxide, ethylene oxide in this case. So if we were able to get ethylene oxide, we would be able to use ethyl magnesium bromide to make that molecule. Well, we've now run into a little bit of a snag, though, because we don't know how to make epoxides. So this synthetic analysis hits a dead end. Presumably it's possible to make ethylene oxide from ethane, but we don't know how. Which means we're actually going to have to use the more convergent version of the synthesis and figure out how to make propyl lithium and ethanol. Well, ethanol almost certainly came from ethanol. probably came from bromoethane through SN2 reaction. Right? So now we're back to something that we know how to obtain. And the only question becomes, from where did propylithium come? Now, propylithium would have had to come from the corresponding organometallic, probably chloride. So how are we going to make that alkyl halide? And now we need actually to introduce a sixth reaction that you don't yet know, which is the topic of the next video, which is how to convert a primary alcohol to an alkyl halide. And I will cheat and give you the answer. Treatment of a primary alcohol with aqueous HBr or aqueous HCl will generate the corresponding alkyl halide from the alcohol. And we know that we can make a primary alcohol from organometallics and formaldehyde. Presumably we can make formaldehyde in exactly the same way as we make ethanol by treatment of methanol with an oxidizing agent. So now we're in a position where we've worked backwards enough that we can turn around and do our forward synthetic reaction. The retrosynthesis can be combined with a forward synthesis in many cases. So you can convert the alkanes into things that you know how to convert alkanes into, and at the same time, you can convert, by working backwards, the complex alcohol, in this case the tertiary alcohol, into simpler precursors, and you hope that you'll come up with the same compound in the middle. So let's work forward. We're starting with methane. We're reacting with bromine under light to make bromomethane. And then we're going to react that with lithium to form an alkyl lithium. But we also know that we can react that with NaOH for methanol, and that methanol can be oxidized with PCC dichloromethane. So we have several different building blocks with one carbon. We also know that if we were to do the same reaction, and it doesn't matter if you use chlorine or bromine, because there's only one kind of hydrogen here, so we don't have to worry about selectivity, we can make the corresponding chloroethane, which could be reacted with magnesium and ether to form the corresponding Grignard reagent, the magnesium chloride salt, or NaOH, a polar protic solvent, to generate the alcohol, which can then be reacted with one of our chromium-6 reagents, maybe PVC, to form ethanol. So we now have two different carbonyl compounds, a couple of different organometallics, and we also now know that it's possible to convert ethanol into ethyl bromide by reacting with aqueous HBr didn't already have bromoethane from free radical bromination. So now what? Well, what we really wanted to react with the ethanol was we wanted propyl, right? Propyl bromide. Reaction of ethyl magnesium chloride with formaldehyde in inert solvent followed by aqueous acid workup will generate the primary alcohol, 1-propanol. And by using the same reaction with APR, we can generate 1-bromopropane. Well, 1-bromopropane is functionally equivalent to chloroethane or bromomethane and can be reacted with magnesium in ether or THF to form the corresponding alkyl magnesium bromide. The combination of this alkyl magnesium bromide with this aldehyde in the inert solvent in which it is formed, the ether, followed by aqueous acid workup, can generate two-pentanol. Oxidation of 2-pentanol, and this time, since it's a secondary alcohol, if we wanted to, we could use aqueous dichromate with no worry about over-oxidation. And we're very close to our final product. All we need now is another equivalent of ethyl magnesium chloride from an inert solvent, like THF as an example, and then an aqueous acid workup, and we will succeed in making our final product. The 3-methyl 3-hexanal that we were after. Hexanol. So it's a lot of steps, but it's only a few different reactions. It's free radical halogenation to functionalize the alkane, reaction with an alkali or an alkaline earth metal to form an organometallic, which now is a source of carbon minus, SN2 substitution to generate the alcohol from the alkyl halide. In this case, both reactions would work well with sodium hydroxide in one of the covalently coated solvents, DMF or DMSO, and then we can oxidize methanol to formaldehyde, ethanol to acetaldehyde, and those carbonyl compounds that we've produced can react with alkyl magnesium bromide or alkyl lithium reagents to form alcohols, which then can in turn be oxidized. So we've got several sequential steps where we're taking a carbonyl compound and adding an organometallic to generate an alcohol, which we then oxidize to form a new carbonyl compound, which is reacting again with another molecule of an alkyl magnesium chloride. That's a pretty complicated example. You probably won't have an example quite that complex on an exam, but the methodology is the same regardless of the